Hello everyone, I am Meenakshi Chauhan and in this lecture I will be discussing about floating point arithmetic operation. In this lecture I will be discussing about floating point addition, floating point subtraction, floating point multiplication, floating point division, some overflow and underflow conditions. So let's get started. Before studying this lecture, students are strongly advised to study a lecture on floating point representation. First, floating point addition and subtraction. For addition and subtraction, whenever two floating point numbers are added, then it is necessary to ensure that both the numbers should have same exponent. If the numbers are not having same exponents, then some alignment process will be done to make the exponent similar. That's why addition and subtraction in floating point arithmetic are more complex than multiplication and division. There are four basic phases of addition and subtraction algorithm. 1. Check for zeros. Second, align the significance. Third, add or subtract the significance. Then normalize the result. Check for zeros. If we are adding or subtracting numbers and then one number is 0, then the other number will be reported as result. If either operand is 0, the other reported as the result. Because addition and subtraction are identical operations except for a sign change. So by changing the sign of subtrahend, the subtract operation can be performed with the help of addition. Next step is to align the significant. And in this process, we manipulate the numbers so that two exponents are equal. So for making exponents equal, we perform significant alignment. Now, once we have made both the exponent equal, now we can add the numbers. So next two significants are added together. So we will add significance taking into account their signs, because if both the numbers are having different signs, then result be 0. And it may be possible that when we add two significance, then overflow may occur. So this is called significant overflow, and significant overflow can be occurred by one digit. When two significants are added and a carry is produced from the MSB bit, then significant overflow occurs. If so, the significant of result is shifted right and exponent is incremented. Once the significant overflow has occurred, then the significant will be shifted right and the power of exponent will be incremented. And this process will be done to remove significant overflow. Whenever the exponent is incremented, then there is a possibility that the exponent overflow may occur. An exponent overflow could occur as a result when the exponent is incremented, and this would be reported and the operation halted. The significant overflow will be removed by aligning the significant or shifting the significant to the right, and for this we will increment the exponent, and incrementing exponent may also cause exponent overflow, and the exponent overflow will be reported. If the final result is not in normalized form, then normalization will be done. And in normalization, the shifting of significant digits to the left until the most significant digit is non-zero. As we have studied in previous lecture how to normalize a floating point number. So in that case, the MSB must be non-zero value, and in binary number system it should be 1. And each shift causes a decrement of the exponent. Whenever we will shift the significand to the left, the exponent power will be decremented, and decrementing the exponent may cause exponent underflow condition, and the result must be rounded off and then reported. For solving the problems of addition of floating point numbers, we will follow the following steps. Suppose two numbers are given, number 1 and number 2, and floating point number are represented in the form significand into base to the power exponent. So we have two numbers, number 1 and number 2. Now the following steps will be followed for performing addition on floating point numbers. Now the first step is to select a number with a smaller exponent. Now we manipulate the mantissa or significant part of the selected number. Once the smaller exponent number has been identified, then we will manipulate the significant or mantissa part of that selected number by shifting the mantissa right by positions of difference of larger exponent and the smaller exponent. And this process is called significant alignment. Next step is to set the exponent of the result to the larger exponent. Larger exponent will be the results exponent. And now perform the addition or subtraction of significand of number 1 and significand of number 2. And after performing addition, we will determine the sign of result. And now final step is to normalize the result if it is not in normalized form. So we will perform these steps. First, two numbers will be given, then we will select the smallest exponent number. Now we will align the significand of a smallest number by the difference of larger exponent and smaller exponent. Now we will set the exponent of the result to the larger exponent. Then we will perform the addition or subtraction which is given. And now we will finally normalize the result if it is not in the normalized form. Now we will take an addition example. So here two numbers are given. One is 270.75 in decimal and second is 3.375 in decimal. And the corresponding binary representation of the both numbers are given. And these numbers will be represented in floating point representation. Both the numbers are in normalized form. Now we will select a number with the smaller exponent. So one exponent is 8 and second exponent is 1. So second number is the smaller exponent number. Now we will manipulate the mantissa part of number 2. So shift the mantissa of number 2 right by larger exponent minus smaller exponent. 8 minus 1 equals to 7 positions. So we will shift the mantissa part of smaller number by 7 positions to the right. The smaller number will be this, and we will simplify the number as. So as you can see that the mantissa part has been shifted to the right by position 7. In this, the mantissa part is shifting to the right. On the other side, the binary point is shifting to the left. So when we will manipulate the mantissa part, we will shift the mantissa part to the right, while we will shift the binary point to the left. Now third step is to set the exponent of the result to the larger exponent. We have the larger exponent 2 to the power 8. So the exponent of the result will be 2 to the power 8. Now we will perform the addition of significance of both the numbers. for the significant of the first number is this, and the significant of the second number which has been manipulated given here. Now we will add the numbers. So you have already studied the binary addition. Here 0 plus 1 will be 1 and 1 plus 1 will be 0 and the carry will be 1. 1 plus 1, 0, carry will be 1. And you will follow the same process to add binary numbers. And the result of the addition will be this. So as you can see that the number is already in normalized form. So we can rewrite this number as, this is the significant part of the addition and this is the exponent part of the addition. Now subtraction example. Subtraction can be performed as addition, only the sign of subtrahend will get changed. Two numbers are given. Number 1, 270.75 in decimal. Number 2, 3.375 in decimal. The respective binary numbers are also given here. Now these binary numbers are represented in floating point representation. Now the first step is to select a number with a smaller exponent. So number 2 has a smaller exponent. Next step is to manipulate the mantissa part of the selected number by shifting it difference of larger exponent and smaller exponent positions to the right. So as we did in the addition example, we will shift the mantissa of number 2 right by 7 positions. So we can rewrite the number 2 as after mantissa alignment. Now we will set the larger exponent 2 to the power 8 as exponent of the result. And now we will perform the subtraction. Significant part of the number 1 is given and the significant part of number 2 is also mentioned here. And we can perform binary subtraction here. So as you have already studied binary subtraction, so you can perform the binary subtraction. Here 0 minus 1. So we will take borrow of 2. So 2 minus 1 will be 1. Now once the borrow has been taken from this 1, it will become 0. 0 minus 1. Again we need some borrow. So we will have 1. Now it has become 0. So 0 minus 0, we will have 0. In this way, you can perform binary subtraction. It is expected that the student already studied binary subtraction, binary multiplication, binary addition and binary division before studying this lecture. Now floating point multiplication. Multiplication of two floating point numbers x and y will be performed using the following formula. The multiplication of these two floating point numbers can be performed by adding the exponent of both the numbers and multiplying the significance of both the number. We follow the following steps to perform floating point multiplication. First, add the exponent of both the floating point numbers. So we will add xe and ye and subtract the bias. Why subtracting of bias? Because the multiplication of two floating point numbers x and y is performed by using following formula. Here x and y are two floating point numbers and we have to perform the multiplication of these two numbers. For this, we will add the exponents of both the numbers and multiply the significance of both the numbers. So to perform multiplication of two floating point numbers, we will follow the given steps. And these steps are add the exponent xe and ye and subtract the bias. Why to subtract the bias? Because when the numbers are represented in floating point representation, then a bias is added with this exponent and a bias value is also added with this exponent. So bias is being added 2 times. So whenever we will add the exponent values, then we will subtract the bias value. Next step is to multiply the two significants. Next, we will determine the sign. The sign will be determined by sign of x XOR sign of y, and this will be the sign of result. Next, normalize the result value. So these steps will be followed to multiply two floating point numbers. Here, multiplication example is given. We have taken two numbers. Number 1 is 270.75 in decimal, and the respective binary value is given here, and this number is also represented in floating point representation. The second number is 3.375 in decimal, and the respective binary is given here. It is also represented in floating point representation. So number 1 is x value and second is y value. This is the significant of number x, which is mentioned here, and this is the significant of y, which is also mentioned here. Exponents of both the numbers are given here. Now we will multiply the significance of both the number, and we will follow the binary multiplication method to solve the multiplication of these significance. So students already studied the binary multiplication in previous lectures. Now the two exponents will be added. 8 plus 1 equals to 9. Here, as you can see that the result is already in normalized form. So we will write the result and exponent of the result. In this way, we can solve the multiplication of two floating point numbers. Floating point division. The division of two floating point numbers x and y can be performed by using following formula. Here we subtract the two exponents and we divide the significand of x by the significand of y. For performing floating point division, the following steps will be used. First, subtract the exponent xe and ye and add the bias, because it has the bias value, it has the bias value included in floating point representation. When we will subtract the exponent, the bias value will be cancelled out. So to represent in floating point, we will have to add bias value. Now we will divide the two significant and determine the sign of the result. The same concept will be applied as in multiplication. The sign of x XOR with sign of y. This will be the sign of result. Now next step is to normalize the result value if it is not in normalized form. In this way, we can solve the numerical problem on floating point division. Here, division example is given. We have taken two numbers. Number 1 is 270.75 in decimal, and the respective binary value is also mentioned here, and this value is also represented in floating point representation. The number 2 is 2.375 in decimal. Respective binary is also mentioned here, and this number is also represented in floating point representation. So we have significand of x, this, significand of y, this. We have two exponents 8 and 1. Now we will divide the significand of s by the significand of y. So we will perform the binary division, and it is shown in this image. So we have to perform binary division of significand of x by significand of y. So we will solve the binary point. So we will move this binary point to here. So to make this number, so for this we will shift binary point from this position to this, because it is having binary point here and we have 4 digits after this. So we will move this binary point to 4 positions to the right. Now we will perform the binary division. As expected, you have studied the binary division in previous lecture, so you can solve the binary division here. Now the exponent values will be subtracted and the result will be, this is the mantissa part of the result and this is the exponent part of the result. Now as you can see that this number is not in normalized form. So we will normalize the result, and for this we will shift this binary point to this position. And when the binary point will be shifted to the right, the exponent will be decremented. So we will decrement the exponent by 1. And in this way, we can solve the floating point division example. Now, overflow and underflow conditions. A floating point operation may produce one of these conditions: exponent overflow, exponent underflow, significant underflow, significant overflow. Now what is exponent overflow? Positive exponent exceeds its maximum possible exponent value. Then we can say the exponent overflow has been occurred. And whenever the exponent is incremented, it may happen that the exponent exceeds its maximum value, and it may be designated as positive infinity or the negative infinity according to the sign. Exponent underflow. Whenever we decrement the exponent, it may happen that the exponent is less than its minimum possible value. So as in example, minus 200 is less than 127. 127, we are considering the bias of single precision representation. So here minus 200 is less than minus 127. 2 to the power minus 200. This number is very small, so it may be reported as to 0 because it is very close to 0. Now significant underflow. In the process of aligning significance, when we have to align significance, it may possible that digit may flow off the right end of the significant. So some form of rounding will be used to remove significant underflow. Significant overflow. The addition of two significants of the same sign may result in carry out of the most significant bit. Whenever the carry is produced from this most significant bit of significant addition result, then significant overflow occurs. And this can be fixed by the realignment of significance. The content of this lecture has been taken from two books. One is Computer Organization and Architecture, written by William Stallingser. Next, Computer Organization and Embedded Systems, written by Sir Carl Hammercher. So in this lecture, we studied floating point arithmetic, in which we studied floating point addition, subtraction, multiplication, and division. And at the last, we studied some underflow overflow condition which may occur during the floating point arithmetic. See you in the next lecture. Till then, happy learning. Thank you very much.